All right, so this mini lecture is going to look at the idea of RC circuits, so resistors and capacitors together in a circuit. And we're going to look at a very simple circuit, just one resistor, one capacitor. And what happens? What's going to take place when this circuit becomes, when I make it a closed circuit by closing that switch? So we're going to imagine that the resistor we're talking about is a light bulb. So our resistor is going to be a light bulb. And then we will talk about when current flows through a light bulb, of course, the light lights. When current is not flowing through the light bulb, the light, of course, does not light. So we'll use that kind of discussion. I'll switch between lit and current, but using that idea of current flowing in the light bulb, lighting, current not flowing, the light bulb doesn't light. Okay, so what happens when I close the switch? When I take this circuit and I move it into this circuit. So immediately when the switch closes, well, we have a potential difference in that circuit, right? So immediately when the switch closes, we know that current is going to flow away from the positive end of the battery and flow towards the negative end of the battery, right? Our current flows in the direction of high to low. And when current flows through that battery, we get light. So immediately we get current in the circuit. How much current? Well, we've learned that the amount of resistance and the amount of voltage determines how much current we get in a circuit. And so initially, the current we get right away is, there's nothing impeding that current. Initially, the current we get right away is going to be related to the voltage and the resistance. V equals IR. That was Ohm's law, right? V equals IR. So the voltage divided by the resistance is going to give us that initial current. But then what starts to happen? When we think about our capacitor, we know that as current flows, as those charges are moving through the circuit, here's my capacitor again, that positive charge, or a high potential, is building up on the same side of the capacitor as the battery, and a low potential is building up on the opposite side as the battery. So we're getting a separation of charge here in the capacitor. We're getting a potential difference in the capacitor. And because that potential difference is in the positives of the battery and the capacitor are together, the negatives of the battery and the capacitor are together. This is like, if you kind of go back to that voltage sources, this is a source of voltage. It's a separation, a potential difference, and they're hooked up in a way that the positives are on the same side. So we start to decrease the voltage available in the circuit. And if I decrease the voltage, what happens to my current? That tells us that the current begins to drop in the circuit. And as the current drops, the light decreases. So it begins to decrease. And as more current flows, more potential difference is built up on this capacitor, more light decreases. And as more current flows, more potential is built up, more light decreases. So the current continues to drop until the point, where the voltage across the battery, we'll say V, is equal to the voltage across the capacitor. So when the voltage across the capacitor is equal to the voltage of the battery, or our EMF, what happens? There's no potential difference. No potential difference in the circuit. No current. And if there's no current, my light, we use the same color, my light goes out. So what happens when we connect a capacitor in a circuit is the light turns on, current flows, nothing's impeding the flow of current, and then as the capacitance builds up in its own potential, the overall voltage of the current of the circuit starts to go down, and we get to 0 volts. Once that happens, there's no potential difference through the circuit, and there's no potential difference across the resistor, and the light goes out. So how does this look? Well, if I was going to plot the current as a function of time, and at t equals 0 is when I drop the switch. T equals 0 is when I drop the switch. I get an initial current related again based on that Ohm's law relationship. Nothing's affecting the current initially. But as the capacitor charges, that current starts to dive off and reaches 0. So this exponential decay describes the charging of the capacitor. This exponential decay describes the charging of the capacitor. Okay? It describes the current. That's a better way to say it, because the capacitor is actually increasing its charge. So this exponential decay describes the current. That's how we want to say it. That'll be a little clearer for us. Introductory way describes the current as the capacitor charges. There we go. Because what I want to now share is, well, how does the voltage across the capacitor look? If the current is decreasing exponentially, how does the voltage across the capacitor look? Well, it should look the opposite of that, right? The voltage, if I look at the voltage across the capacitor as a function of time, we should see that the voltage across the capacitor increases, starts at 0. There's nothing across the capacitor when we first put the switch closed, increases as a function of time. So this exponential growth describes the voltage as the capacitor charges. All right. So now we're going to look at, well, this first, before we look at what happens then when I open the switch up again, let's put these ideas into equation form based on exponential growth and decay. I'm going to leave this circuit up for a minute. I'm going to give you the relationships that we're interested in and a little bit more vocabulary. So the current through the circuit, through an RC circuit, is equal to my initial value of the current, where that initial value is equal to the voltage or the EMF. We're going to just deal with voltages, and divided by the resistance, so that's based on Ohm's law, times e to the minus t, time, as time goes on, over the resistance times the capacitance. Okay, so we've determined that that is the relationship for how the current behaves in an RC circuit while the capacitor is charging. Now, there's a little bit of name here. This value RC is defined as the time constant. And the time constant is defined, and I just want to get this right, is the time it takes. You might remember this from learning about exponential decay and growth. The time it takes for the current to reach 1 over E, which is about a third, 0.37, of its max value. Okay, so that's sort of our definition of time constant. So this is in general, but for here. So this is going to be our current in an RC circuit. And the voltage across the capacitor, now that's growth. That's the voltage across the battery times 1 minus E to the minus T over RC. So we start off with at time equals 0, this term goes to 0, and we start off with the, this goes to infinity, so we start off with the voltage across the capacitor being 0, so this number goes to 0, this goes to 1, if this is 0, this is 1, this goes to 0, there we got it. The voltage across the capacitor is 0, and as time goes on, we get a proportion, 1 minus, so a percentage of the voltage as the time grows. All right, so this is a little fumbled up there with my math. This is the voltage across a capacitor during charging. Okay, so during charging. All right, so write those equations down so that you have them easily accessible for use. All right, so this is where we were at, right? So this was the circuit that led to all of this. Right, we closed that and we were at this situation. So now there's no current flowing. It's a long time later, there's no current flowing in this circuit. The light bulb, therefore, is out. What happens? Let me erase this first. If we go through a little stepwise process where I open the circuit, disconnect the battery, and then close the circuit. What do you think might happen if I open the circuit, disconnect the battery, and then close the circuit? So I'm erasing this. I want you to kind of make a prediction in your head. Okay, so the process is first, I reopen the circuit. Oops. I take this switch and I get rid of the battery altogether, and I'm left with a resistor and a capacitor alone. What happens? Well, think about the situation that we have. When we are in this situation after charging, this capacitor has a high potential and a low potential equal to the voltage source. So remember, the capacitor's voltage is now equal to the voltage of the source. Okay? Well, that's like a little battery. A charged capacitor now behaves like a battery, a voltage source. So when I close the switch, taking out the battery, you can't see me taking out battery, but if I close the switch and take out the battery, so just write that if you're just kind of trying to keep track. And I have a little battery. I have a potential difference in the circuit, high to low. And if I have a battery, if I have a potential difference, the bulb lights, current flows. But the source of these charges are the plates of the capacitors, and as current flows, what happens to those plates? Well, the plates, the capacitor, starts to lose charge. And as it loses charge, it decreases its potential, the potential across the capacitor. And as that happens, we decrease the current. And as that happens, the lights go out. Not suddenly. Remember, the capacitor is discharging at the same rate it charged. Our capacitor, if we look at the current as a function of time, when I close that switch, it does the same thing. When I close that switch, the current decreases. So the current for charging and discharging looks the same. All right? So as time goes on, the current decreases, the lights go out. What about the voltage? What's happening to the voltage across this capacitor? Well, it too is decreasing. And because of the way that the current is decreasing, the voltage across the capacitor is similar. It too decreases as time goes on. So our voltage across the capacitor is equal to our initial voltage, which, if fully charged, was the voltage of the source, and follows the same decay rate as our current. All right. So the idea behind these capacitors is they take some time to charge, related to our time constant, which is related to the capacitance, right? And the resistance, okay? And why that might be? Well, because we know that resistors influence the current in a circuit. So it stands to reason that they're going to have some play over how quickly that capacitor can charge. Capacitance, of course, is how much charge it can hold. So that does, I hope, make a little bit of intuitive sense. Now it could have influence over how long it could take to charge. When charging a capacitor, the current starts high because nothing is impeding that flow. And as the potential difference across the capacitor increases, we get the potential in the circuit decreasing. Current needs to decrease based on how fast that capacitor is charging. Conversely, when a capacitor is charging, we're increasing in its voltage, the potential difference across that capacitor, at the same rate that the current is decreasing, but it's a growth situation. I guess it's not called exponential growth, it's 1 minus exponential growth. For a capacitor discharging, we start off, it's like a mini battery right away, but as the charges leave the capacitor, the potential difference across that capacitor goes down. The current in the circuit then also has to follow suit, and we see similar between the decay in the current and the decay in the potential across the capacitor. All right, let's use this in an example just to play with these terms. I will mention one more thing about this value RC. You will also see that written as a lowercase tau in here, and actually in a lot of things where we talk about a time constant. Tau is often the variable we use for a time constant. So just want to share that with you as well. So let's do a quick example using these new equations in the analysis of an RC circuit. Get this all erased. actually kind of challenging to erase this board and get a good arm workout. Unlike those dry erase boards in my classroom. All right, done. Okay. Let's look at a practice problem dealing with charges. So I'm going to draw the circuit that's being described. So we have a voltage source. Oops, that's not what I want. Here's my switch. So it looks very similar to the one we just had. And here's point A, here's point B, and that's my switch S. All right. Voltage source here, that's our long line and short line, our little jaggedy resistor. Here's our capacitor. We are given that the volts in this is 20 volts. And the resistor is unknown. That's the question that's being asked. The resistor is unknown. And the capacitance is equal to 1.02 microfarads. So remember that's 1.02 times 10 to the minus 6 farads. All right. So what happens when the switch is thrown from the switch is thrown to point A? We want to describe what happens, so we'll talk through that. And after a long time, hint, a long time, the switch is thrown from A to B, right? It's observed when that happens that the current decreases to 50% of its original value in 40 microseconds. So 40 times 10 to the minus 6 microseconds. What happens when that switch is first thrown? So what happens when I go from A to B? And then let's determine the value of the resistor. So we're first going to describe what we see, what we would see, what we'd expect to see, and then we'll analyze what is the value of this resistor. Let's imagine that the resistor is a light bulb, and we'll use light, of course, as our visual of what we might see. So throw the switch to A. It's the first thing that happens when I throw that switch to A. Well, current flows in the circuit. We have a potential difference. This open air of B it's an open circuit, so nothing goes there, nothing happens there because it's open, okay? So I know when you do circuit analysis, you kind of get to a junction, you're like, ooh, what happens? But if there's nothing connecting, there is no circuit. So we can imagine as if that B isn't even there. We throw that switch, nothing impedes the current flowing, and we light the light bulb. Over time, however, the capacitor is building up charge. The potential connected to the positive side is getting more positive. The side that's connected to the low potential of the battery is getting more negative, lower, if we want to just think about it in relative terms, until these two match. So as it does that, as the voltage in the circuit starts to decrease, the current in the circuit starts to decrease, and the light bulb starts to dim until those two are equal and the light goes out. So that's that decay that we see in the current. If we use current, if the light bulbs light the brightness, for example, as a reflection of the current. All right, now the light's out, sitting out there. Long time passes, it's just hanging out there. Nothing is charging anymore because the capacitor has reached the potential of the source, and therefore there's no force exerted on these charges and these free electrons in the wire anymore, and they just hang out doing nothing, and no current is flowing. Okay, then we switch, and our circuit connects to B. Now the battery's out of the picture. And what happens? Well, the capacitor, it acts like a battery. And the light turns on, and as that capacitor starts to lose its charge, because the potential difference across that capacitor is causing those charges to flow, the charges are no longer being built up, they're decreasing on those plates, which means they are less and less of a potential difference across those plates, less and less voltage, less and less current, and the light dims to nothing. So flip the switch, bright, dims to nothing, close the switch, change the switch, bright, dims to nothing. So just observing the dimming to nothing, we actually don't know if the capacitor is charging or dissipating. So that's an important kind of safety feature because we certainly don't want to be involved in dissipating a large capacitor, right? So that's like touching a high voltage source and it dissipating through you. We're resistors. So it's a little preview to some safety stuff. All right, so that's what happens in a descriptive way. Well, what's the value of the resistor in this current, in this circuit? All right, so now we're going to use the equations that we've just been playing with. So we know that our current, whether charging or discharging in a capacitor, is equal to the initial current, which is determined by Ohm's law in a simple RC circuit, times e to the minus t over RC. So this is our base equation. We are told that it reaches 50% of its original value. If I wanted to know the original value, remember I naught is equal to the voltage over the resistance. I don't know the resistance. So I can't get a number for that original value, but I'm told that I equals 50% or half of I naught at 40 microseconds. So we can look at 0.5 I naught is equal to I naught e to the minus 40 microseconds, or 40 times 10 to the minus 6 divided by R, and we're given coulombs, which is 1.02 times 10 to the minus 6. All right, so that's kind of nice. My I naughts cancel. And I'm left with 0.5 equals e to the minus 40, e to the minus 6. I'm leaving it in this form on purpose. R times 1.02 e to the minus 6. How do I get rid of that e? Whew! Bring back that math. We take the natural log. So the natural log of 0.5, the natural log of e is the value in its exponent, is equal to minus 40 times 10 to the minus 6 divided by R times 1.02 is 10 to the minus 6. The natural log of 0.5 is negative 0.693, negative 40 e to the minus 6 over R times 1.02 times 10 to the minus 6. I'm going to bring R over here, divide by negative 602, and I end up with R equal to 57 ohms. All right, so I can determine the resistance in that circuit if I know the time it takes for the current to reach a proportion of its original current. Okay, so kind of utilizing these new equations, the descriptive thing pretty important in terms of sort of making sure you're thinking about these equations properly. Could certainly ask, now that I know the resistance, what is the time that it takes to reach full capacity? So that would be the resistance times the capacitance, for example. So a lot of different ways to think about how this circuit behaves and representing it mathematically. Good job.